Hi, everyone. I'm Phillip, and I'm going to talk about when and why does contrastive learning work. Okay, so first, what is contrastive learning? So contrastive learning is a really popular method right now. It's a great way of learning when you don't have labeled data. And I'm going to illustrate it with the SimClear method, which is one of the popular approaches. Okay, so what SimClear does, as illustrated by this graphic that they made, is you try to learn a representation of an image, meaning a mapping from the image to a low-dimensional embedding vector. And you want to learn a representation such that two different crops into the same image end up getting attracted to each other. So different parts of the image get represented alike. And two different crops from two different images end up getting repelled from each other in embedding space. And more generally, we can say we want two different views. A view could be a crop into the image, or it could be a different color channel. Two different views of the same image should map to the same embedding representation. And two different views of different images should map to different representations. Okay, so this method is working really well for self-supervised learning right now. It's a hot topic. It's also an old idea. This idea goes back to the 90s with methods like Becker and Hinton, which is essentially SimClear, but without deep networks. Okay, so the objective function that we will be looking at in this talk is the contrastive objective of the following form. The goal is to learn an embedding function f that will pull together two views of the same scene and push apart two views of two different scenes. Two views of the same scene are called positive pairs, and two views of two different scenes are called negative pairs. Okay, so we have x and y, which are sampled from the positive pair distribution. These are two views of the same scene, two different crops into the same image. The numerator will try to increase the similarity of two views of the same scene, and the denominator will try to force two views of two different scenes, y and x negative, sampled from a different scene, to map to different points in embedding space to be pushed apart. Okay, so why does this objective work so well? That's going to be the focus of today, of my talk. I'm going to try to give three quick explanations. Okay, the first is going to be a very classic idea. It goes back to the 90s. It actually goes back way, way farther. It goes back to the 2090 BCs. This is Plato's allegory of the cave. Okay, so what he said is that you can imagine a cave with prisoners, and their only experience of the outside world is the shadows cast upon the wall of the cave. And it's an allegory because Plato is saying that this is really how we experience the world. We see a cow, but we don't have access to the actual cow, right? We don't know the Platonic reality, the physical thing that generated the cow. We just have this superficial glimpse of the cow, the light that plays across its surface. The same, we might hear the sound of the cow, the moo. It's not the cow itself, it's just a sensory measurement of what is going on in the actual physical Platonic reality. Okay, we can call that reality the state of the world, and the state is thought to cause the observations that we see. It's a causal generative model of the observations that we see. The cow generates a photo and it generates a sound. And the goal of a lot of work in representation learning is essentially infer the state, infer the cause from the observations. Okay, so learn the mapping from the observations of the cow back to this Platonic state. And what contrastive learning can be understood to be doing is essentially skipping the generative modeling part of the process and simply trying to align different co-occurring sensory measurements of the same underlying state. Okay, so we might have the sensation of touch of the cow, the picture of the cow, the sound the cow makes, and all of these co-occurring sensory measurements, we try to learn to align them, to map them to a common embedding vector, and that ends up being a way to infer kind of a common cause that could have created all of these sensations. Okay, so this is a classical explanation, but it's one I really like a lot, so I wanted to start with that. It's an explanation from causal inference that contrastive methods that try to align multi-view data end up trying to infer the common cause underlying all of these co-occurring views of the world. So more recently, what's become popular is to understand contrastive learning with information theory. So I'm going to turn to that next, and I'm going to talk about our work on what makes for good views for contrastive learning. This is work with Yonglong Tian, my student, and collaborators at Google, Dilip, Ben, Chen, and Cordelia. Okay, so let me introduce the information theoretic story of contrastive learning. This was popularized by the Info NCE objective in the Van de Oorn et al. Paper, CPC. Okay, we have the same setup as before. We have two different views of an image, maybe a crop of the tiger and another crop of the tiger. We're going to try to learn embeddings Z1 and Z2. And what they showed in the Info NCE paper is that the contrastive objective, the same one that I showed before, is a lower bound on the mutual information between the embeddings of the two views. Okay, and by the data processing inequality, the mutual information between the embeddings, between the representations, is strictly less than the mutual information between the raw views themselves, because the embeddings are a deterministic function of the views v1 and v2. Okay, so if we try to minimize the contrastive loss, the effect that has is it will maximize the mutual information we capture in the embeddings. Okay, so here is the total mutual information that you could capture between V1 and V2. And as we minimize our contrastive objective, we do contrastive learning. We will try to learn a representation that captures all of that information in our embeddings. So this is the InfoMax idea of contrastive learning. And what's really interesting about this to me is that it tells us that what determines what you learn when you do contrastive learning is the mutual information between V1 and V2. And V1 and V2 are choices, are modeling choices. We get to decide what are going to be the views of the world that we try to align with contrastive learning. And that will determine what we learn, because we'll learn the mutual information between those two views. Okay, so in this paper, what we did is we wanted to ask what happens when we change our selection of views? What are the best views that will lead to the best representations? So I'm going to show one of the experiments that we did here. We constructed views, which are crops of an image. And we varied the viewing conditions to be crops at different spatial offsets. So two overlapping patches or two far apart patches. As we increase the spatial distance between the patches, the mutual information between the two views will go down. So on the x-axis in the plot that I'm going to show, we have an estimate of the mutual information between two views. And on the y-axis is going to be a measure of the representational quality when you apply contrastive learning on top of those two views. We're going to be using the standard method for measuring representation quality, which is transfer learning. We see if when you fine tune on top of your learned representation toward a downstream task like classification, do you do well? So here is the curve that we saw. It's kind of a reverse U-shape. The number indicates the number of pixels between the two patches. So when the views are very far apart, they don't overlap at all. You have not much information shared between them and low transfer accuracy. When they overlap almost completely, you have a lot of shared information between the views, but also low transfer accuracy. And it turns out that there's a sweet spot up here where the two views have just the right level of mutual information to capture just the right bits of information. Okay, so that's empirically interesting, but maybe it's a one-off. But we tried this, again, on a different set of views. In this case, we constructed views as different color channels of an image. So again, I'm going to plot the mutual information between the two views, where the views are now different channels in different color spaces. The R channel, the luminance channel, the hue channel, the saturation channel, etc. But we're going to make a scatter plot, and it looks like this. Again, we have this reverse U-shaped curve. So here's 2 points to contextualize this. We have the RGB color space. R, G, and B are very redundant. They share a lot of information with each other, so they have high mutual information between those color channels. As you decrease the mutual information and choose a color space in which the color channels are more independent of each other, like the YDBDR color space, you end up getting a better representation. Okay, so there's this interesting sweet spot of mutual information. Intermediate levels of shared information between the two views lead to the best representations. We want to understand why that is. There's actually a lot more experiments in the paper showing that reverse U-shaped curve shows up in other settings as well. But let me move on to why I think this might be happening. So I'm going to plot now. On the x-axis, again, the same exact thing, the mutual information between two views, view 1 and view 2. And then we're going to show how this relates to other measures of information. So first we'll plot I v1, v2 with respect to itself. That's just the identity function. So as we choose different views at different distances, we'll lie on different points on this line. But we don't actually care about the mutual information between two crops. We care about the information between an image and a task. We're going to use our representation that we learned to solve some task like semantic segmentation in this example here. So our image is X, our views are V1 and V2, and our task is Y. We don't know what the task is in general in advance, but for analysis, we can assume there exists some downstream task that we will care about. Okay, so the mutual information between an image and the task, the semantics, is going to be some number of bits. And as we change the views, we will at some point have less bits than exist between the image and the task, and at some other point we'll have more bits. And we get these three kind of regimes of information, where as we vary our views, if the views have less information shared between them than the total number of bits shared between the image and the task, we must be missing some critical information to solve the task. Okay, then there's a sweet spot where we capture just the right information, and in theory, we could capture all the information relevant to the task. And then later, we will have more information than exists with respect to the task, and so we must, in the two views, be capturing some irrelevant noise, something like background details or lighting conditions that might be irrelevant to the task. So theoretically, we can have either a regime of missing information, excess information, or having captured just the right amount of information. And we hypothesize that that explains why, when we vary the mutual information between the two views, you get this reverse U-shaped function. So if you don't have enough information shared between the two views, then you don't have sufficient information to solve the task. You don't have enough signal. And then if you have too much information shared between the two views, you now have redundant information that you're encoding, and this acts as noise and reduces your ability to generalize because you're going to be overfitting to that noise. Okay, so what you want is a representation which is not too big and not too small. It captures the sufficient amount of information to solve the task, but no more. It's minimal and sufficient. This is actually an idea that was put forth by Sawato and Chioso a few years ago, and also shows up in the information bottleneck theory of Tishby et al. So our explanation from information theory is that if you select your views for contrastive representation learning properly, then you can select them such that their mutual information will be minimal and sufficient for solving the downstream task you care about. And in some settings where this contrastive methods have been successful, we think that we might be near that sweet spot. Okay, the last explanation I'm going to give is an explanation from geometry. And this is work that was led by Tongzhou Wang on understanding contrastive representation learning through alignment and uniformity on the hypersphere. So Tongzhou wanted to look at the geometry of the embeddings learned by contrastive methods. The first thing to note is that contrastive methods generally map to a normalized space. That means we're mapping to embedding vectors that lie in the surface of a hypersphere. So in a toy experiment, what he did is he trained encoders with a contrastive objective on CFAR10 to map to a one-dimensional embedding space, in other words, to the surface of a circle. And now we can visualize the distribution over embeddings in representation space on the CFAR10 validation set, and it looks like this. It looks like a uniform distribution over the circle. Okay, what if we had instead trained a CFAR10 classifier with the cross entropy loss, regular old supervised learning? Well, then your embedding vectors that would appear in that neural network would have a less uniform distribution. Or what if we started with a randomly initialized encoder? Well, a randomly initialized encoder will make a very non-uniform distribution. So it looks like something about contrastive learning is taking us from this randomly initialized non-uniform distribution to this nice uniform distribution. Why is that happening? So we came up with a metric for uniformity to try to understand this. And we also came up with a metric for alignment, which is just a rephrasing of the classic contrastive objective of trying to map two views of the same scene to the same point. Okay, so alignment measures the distance between the embeddings for view 1, x, and view 2, y. And uniformity measures, just on average, how far apart are the embeddings for different images. Okay, so when we sample different images from our data set, IID, and we embed them into feature space, we can measure this kind of Gaussian potential, the expected exponentiated distance between those embeddings. And the uniformity measure is minimized when you've mapped to a uniform distribution. Okay, so it turns out that if you write out the contrastive objective, asymptotically, you can rearrange the terms and observe that it's related to these two metrics, alignment and uniformity. So here's the contrastive objective. This is our info NCE objective. And it turns out to be equal in the asymptotic limit as the number of negative samples goes to infinity to a term related to the numerator and a term related to the denominator. And the numerator term is minimized if and only if f, the encoding, is perfectly aligned, meaning f of x and f of y are identical. And if perfectly uniform encoders exist, they form the exact minimizers of the second term. Okay, so the contrastive objective, in other words, can be understood as the composition of two properties that we might care about, alignment and uniformity. And asymptotically, minimizing the contrastive objective will result in aligned and uniform representations if that is achievable. This explanation is actually quite related to the explanation from information theory, but it turns out to be a little bit stronger. So the explanation from information theory says that contrastive learning results in maximizing the mutual information between the embedding for one view and the embedding for the other view of the same image. That corresponds to minimizing the conditional entropy between the two views and maximizing the unconditional entropy of the views. Okay, uniformity maps to a max entropy distribution. The max entropy distribution is the uniform distribution. But alignment is actually stronger than just minimizing the conditional entropy, because it could be you minimize conditional entropy by just making f of x perfectly predictable from f of y via a very complicated function. Alignment says, no, it can't be a complicated function. You actually have to have nice geometry in the embedding space where f of x and f of y are not just they share information, but they're actually the same vector. So this is a stronger condition than the conditions imposed by the information theoretic argument. Okay, so we've proposed that good representations are aligned, meaning two different views of the same scene mapped to the same point in representation space, and uniform, the embeddings for random images mapped to a uniform distribution. We can run the same exact experiments that we ran in the other work, where we look at transfer performance for different representations. So on the x-axis in these plots, we have the uniformity metric, and on the y-axis, we have the alignment metric. And in color, we have transfer performance. How good are these metrics when you transfer them? How good are these representations when you transfer them to a new task? And it turns out that aligned and uniform representations end up achieving the best performance at transfer to classification task or at transfer to depth prediction task. And actually, we've run this in a bunch of other settings too on language data sets. You get the same story. Good representations are those that are both aligned and uniform. So this is my third explanation from geometry. Good representations are aligned and uniform. And yeah, I'm sure that there's a lot more beyond this that one could use to explain contrastive learning. These are not independent explanations, they're interrelated, but the three that I've identified so far are contrastive learning is a way of doing something kind of like causal inference, inferring the common cause of co-occurring observations. With properly chosen views, you end up learning representations that may be minimal and sufficient for the downstream tasks that you care about. And these representations have nice geometric properties like being aligned and uniform. So I will end there. I'll thank my collaborators, Yonglong Tian, Tongzhou, Phillip, Ben, Chen, and Cordelia. And thank you for listening.